first do some examples of the chain rule and later see how the chain rule helps us differentiate really complicated functions, and I'll show you technical logarithmic differentiation. So always rely on the chain rule. I'll remind you what the chain rule is. Chain rule. The chain rule was about a composition of two functions. F of, but not f of x, but rather f of some other term, g of x. We usually call this the external function and this one the internal function. And the answer was the derivative of the composition is derivative of external function evaluated its argument, which is g of x, multiplied by the derivative of the internal function. Or, well, we want to say, if you have one function of its parameter b, and b itself is a function of x, then the derivative of u relative to x, so derivative of the composite function, the function u as a function of x, is the product of two derivatives. Derivative of du by dv, derivative of u relative to its parameter, multiplied by derivative of b relative to its parameter x. Let's start with some simple example, something like what we did last lecture, or even 2 lectures before this. An example. There's a function logarithm of sine of x. What would be the derivative of this? So I'm asking either for the answer or how to start with it. What should I denote by u? What should I denote by v? What kind of derivatives they should complete? Yeah.
U would be involved.
Okay, so last operation I'm doing is compute logarithm of something. So my last operation is logarithm of v. And v sine of x. So I'm computing logarithm of sine of x. So I choose u to be logarithm of v and v to be sine of x. And then I just use the definition. So du, sorry, not the definition, but rather the chain rule. Du by dv, derivative of logarithm was 1 over v. Derivative of sine is the cosine. So what is the answer? One over sine times the cosine. So the only additional piece of information here is v. I don't want to keep v in the answer. V is just an intermediate step for me. It's some auxiliary function that I introduced in the beginning. I want to write that v is in fact sine of x in the answer. Okay, so that's how the chain rule works in concrete examples. We choose what is the internal function, what is the external function, in such a way that their composition is indeed the original function. So if you take one of and substitute that v is sine of x, you should get the original expression, apply the chain rule, and you get the answer. So last time we've seen also some tricks about, in the very end of last time, we found the derivative of a function which was something like 5 to the power x. Something which doesn't look like a composition, but it is a composition in disguise. So let's do some example or rather a useful trick. Differentiating f(x) raised to the power 2x. So look on an example. Let's say I want to differentiate the function x raised to the power x squared plus 1. A reasonable function. I take the number x and raise it to the power x squared plus 1. So for example, this function relates to the next equal to 2 will be 2 raised to the power 2 squared plus 1, which is 5. So 2 to the power 5, 32. And you can do this operation well for any x. You can take any x and raise it to the power x squared plus 1. The thing here is, it's not in the form, in one of the familiar forms. It's not, well, x raised to some constant power. It's not x to the power n. You can differentiate it using the rule n times x to the power n minus 1, just because the power to which you are raising is changing with x. It's not a number. It's not an expression like x squared, not like x cubed. It's x raised to the power which depends on x. It's also not of the form e to the power which depends on x. This thing, well, it's not e. So the question is, what can I do about such an expression? Oh, another thing, it doesn't look like a composition of two functions. Just because, well, here you have something that depends on x raised to something else which depends on x. So it doesn't seem that you can write this as a composition of functions of just one parameter. Because this operation of taking one thing and raise it to another thing is kind of function of two parameters, not one. So it doesn't seem like we can apply the chain rule directly. Does anyone remember the trick from very end of last time when we differentiated 5 to the power x? Yeah.
You can log it.
Yes. So the idea in the end of last class was, well, 5 was not quite e. And we tried to find what is derivative of 5 to the power x. Well, we know what is derivative of e to the power something. So we wrote 5 as e to some power. Well, the nice thing is you can write anything as e to some power. Here's an example. X is e to what power? Logarithm of x. By definition, logarithm of x is the power to which you should raise e so that to get x. Okay? So let's use this. Let's rewrite this as e raised to the power 1x, then raised to the power x squared plus 1, and then derivative. So this is this step. Next I will use rules for powers. A to the power b and then raised to the power c is the same as a raised to the power b times c. So here I'll use this quantity. So here I'll write this 1 of x multiplied by x squared plus 1. And now I'm trying to find the unit. Okay, next step. How can I find the derivative of this thing? Now it is of the form e, some number which does not depend on x. It's just a number, 2.718, and so on and so on. Raised to a power which does depend on x. So what rule should I apply now? Now we are ready for applying one closed differentiation rules. We know what is the derivative of e to the power x. What we have here is e raised to power which is not quite x, but some function which depends on x. Product rule. So this is the last operation that we are computing here, the product. What is the last operation? E to the power, yes. So, but it's not just e to the power x, it's e to a complicated expression. So what rule do we have for being both expressions one at a time? The chain. Thanks. So that's exactly the situation we have here. We have, well, in this example, we have logarithm of not quite x, but rather a complicated expression in terms of x. Same here. It's e raised not to power x, but rather some complicated power in terms of x. So what we do is we choose u, the last operation to be performed, to be e to the power b, and b is 1x times x squared plus 1. We also have to find what's du by dv. To apply the chain rule, let's see what's the derivative of e to the power b. What's the derivative of e to the power b? E to the power b, yes. Thanks. So you know that derivative of e to the power x is e to the power x, derivative of e to the power b with respect to b. It means just we think about v as the parameter is e to the power b. Okay. We also should compute dv by dx. Well, that might be not as simple as the previous computation, but still simple enough. So how can I find the derivative of this expression? What's the last operation that I'm performing here in this computation? So when I have the expression ln of x multiplied by x squared plus 1, what is the very last operation that I'm performing? The product, yes. So after computing logarithm of x and computing x squared plus 1, I have to compute the product of the two answers. So since this is the last operation, the corresponding rule will be the product rule. I see this as a product of two expressions, and I apply the product rule, derivative of first expression times the second expression plus first expression times derivative of the second one, 2x. So overall, I have the following answer. E raised to the power 1x times x squared plus 1 multiplied by, that's e to the power b, multiplied by dv by dx, which is x squared plus 1 over x plus 2x times 1x. So more generally, you can find, well, what is the derivative of any function depending on x raised to any power that depends on x. And the trick is to do exactly the same procedure. So generally, more generally, if you want to find what is derivative of f of x raised to the power 2 of x, well, let's do it quickly. I will write it as e to the power 1 f of x multiplied by g of x. So instead of writing f, I will instead write e to the power 1f. Of course, so exactly like we did for x, but now we do it for f. And now just apply the chain rule. Choose u to be e to the power v, v to be 1f times g. Compute du by dv. That's e to the power v. dv by dx. Well, you have to apply the product rule, so it's 1 over f of x times g of x. So, okay, that's fine. dv by dx. That's actually a good computation. Let's find what's dv by dx in the most general situation right here. So the last operation that I'm performing here is the product. It's 1 of f times g of x. So the product is the very last thing that I'm doing. So I apply the product. I started applying it, but well, let's do it slowly. So it's the derivative of first factor times the second factor plus the first factor times derivative of the second factor. I can simplify it a little bit more. I can find what is derivative of 1 of f of x. So right here, I have this derivative that I still didn't evaluate. Let's do it. Let's evaluate this derivative. How can I find this derivative? Would it be correct to write that it's just 1 divided by f of x? What would be the objection to this? Why I cannot write that it's 1 over f of x? After all, the derivative of logarithm is 1 over its argument, so why not? Yeah.
This is still a function, so you have to use the chain rule.
Exactly. So, like we had here, we had logarithm of a function that depends on x. Well, we couldn't just say that the derivative is the derivative of logarithm. It's not just 1 over f of x. It's not just 1 over whatever was inside the logarithm. It's 1 over whatever was inside the logarithm multiplied by derivative of whatever is inside the logarithm. The chain. So here, once again, we apply the chain rule. With u being 1 of v, and then we get s. du by dv is 1 over v, dv by dx being 1 of x. And the answer would be 1 over f of x times f prime of x. So now once I have all the intermediate computations, I can go back to here and here I apply the chain rule. So we copy the answer. So the answer is, well, somewhat complicated. E to the power b right here, e to the power 1 f of x multiplied by g of x, multiplied by dv by dx, multiplied by this whole expression, and I'll have to plug in whatever I computed there for the derivative of 1 f of x. So it's f prime of x and g of x divided by f of x plus g prime of x times 1 f of x. So something quite complicated. If you want, you can simplify it just a little bit. After all, this expression is something that we already encountered. E to the power 1 f of x times g of x is just f of x raised to the power gx. But the other part, well, it's a complicated expression. So in general, we will not ask you to remember such a formula. It's a horrible formula. But what you should remember is the general method behind obtaining this formula. Every time you have a function that depends on x raised to the power, which is itself a function of x, rewrite the base, rewrite this f of x as e raised to the power logarithm of f of x, like we did here. And then apply the usual set of differentiation rules. The chain rule, the product rule, maybe the chain rule once again. And this will lead you to the answer. Please, any questions about either the general way to find the derivative of f to the power g, or well, the example, or maybe any other examples you have in mind? Yeah.
How did you come up with like the time to the chain rule max? And the product rule is behind the chain rule.
So I just copied this expression, but instead of 1 f prime, I substituted the answer f prime over f. I think it's right. So once again, there is no need to remember this formula. I personally don't remember this formula, but I do remember the general idea. If you have an expression in terms of x, write it as e to the power 1 of x. By the way, this method applies even to familiar functions. Like if, for example, you look at function x to the power 5, and for some reason you forget that it's just x to the power 5, just x to the power, a power that does not depend on x, you can still apply this trick. So let me write a stupid example. It's stupid in the sense that you'll spend much more time than necessary to find the answer, but it's not stupid in the sense that it will show that everything that you do is in fact consistent. So for example, let's find the derivative of x to the power 5, but not using the usual method, not just say that it's 5 times x to the power 4, but using this trick. Should be rather easy. What is x? Well, it's e to the power 1x. So we are computing the derivative of e to the power 5 times 1x. Well, of course we should apply the chain rule. The function u, which is e to the power v, and v being 5 times 1x. du by dv, well, that's e to the power v. dA by dx, that's also easy. What is dA by dx? 5 divided by x. So derivative of 1 of x is 1 over x, and 5 is just a constant multiple. So let's write the answer. E raised to the power v, 5 1x, multiplied by 5 over x. Okay, that's the answer. Is it the answer that we expected? We expected, after all, 5 times x to the power 4. Is it? So here an answer, no. Let's see. can you simplify this expression? E to the power 5 1x. Exactly. So I can write this as e raised to the power 1x and then raised to the power 5. Exactly what we did here, but in the opposite order. So going from here to there. And now we'll go from here to here. I'll write that e to the power 1x is just x. X raised to the power 5 multiplied by 5 over x, which is 5 times x to the power 4. So, no surprises. You still get the correct answer, well, the only answer which is possible to get is everything correctly. Of course, you shouldn't do this computation in this way. I mean, on an exam, save the time and write the answer 5 times x to the power 4. Don't overcomplicate things. In the same way, like here, I did not apply the product rule, I applied the constant multiple. Applying the product rule will not be a mistake, but it will take more time. Okay, so please, questions about this example? Now I want to discuss something a little bit theoretical. If you recall, when we discussed logarithms, well, we introduced what logarithm was. We drew the graph of logarithm. But then, in the very end of the lecture, when we discussed logarithms, I just told you the derivative of logarithm of x is 1 over x. And I told you, well, unfortunately, at this point, I cannot justify. Well, now we are at the point where we can justify, so let's do it. Computing. Well, here's the trick. We define logarithm of x to be the power to which you should raise e to get x. So logarithm of x was basically defined by such an identity. X is exactly the same as e raised to the power 1x. Well, this identity holds for any x. So on the left you have a function of x, which is just x. On the right you have a different function of x, e to the power 1x. But they are, well, they are different expressions, but exactly the same function. Behave exactly in the same way. So in particular, their derivatives are exactly the same. X prime is the same as e to the power 1x prime. Oh. Let's compute both sides. Derivative of x is just 1. Derivative of e to the power 1x, well, I have to apply the chain rule. I know what's the derivative of e to some power. It's e to this power. But then I have to multiply the derivative of the internal function, which is 1x. My point here is I pretend that I don't know what is the derivative of 1x. And in a way, well, up to this point you just have to believe me that somehow I'm sure the derivative of 1 of x is 1 over x. Now you don't have to believe me. I just apply the chain rule, and here's the derivative of 1 of x. So here I apply the chain rule in the form u was e to the power v, v was 1 of x. Well, now, what is e to the power 1x? That's just x. So what's the derivative of 1 of x? Rearrange this. It's 1 over x. So the fact that the derivative of logarithm of x is 1 over x, well, it's not something that has to be, I don't know, re-derived from first principles or has to be predicted or something like this. It's a simple consequence of definition of what logarithm of x is and the chain rule. And that's it. These questions about this computation. Once again, the point of it is not the final result. We already know the final result, but the way to get the final result. In this computation, we did not rely on our knowledge that the derivative of 1 of x is 1 over x. We relied on simpler facts, the definition of logarithm and the chain rule. These two things together give you what the derivative of logarithm is. So next thing I want to discuss is applying the chain rule in situation where you don't quite know what the function is. You only know something about this function. So the next example on the chain rule will be like this. Suppose that g of x is, let's say, f of x squared plus 1. Suppose I also know that f prime at the point 10 is pi. And the question is, what is g prime at the point 3? So I have no idea what the function f is. As a consequence, I have no idea what the function g is. The only thing I know is how f and g are related. So g is f at the point x squared plus 1. And I know that the derivative of f at the point 10 is 5. Question is, what is the derivative of g at the point 3? That's all. So I want to find g prime at the point 3. I'll first try to find how g prime at point x is related to derivatives of f. I know that g is related to f, so I assume that derivative of g would be somehow related to derivative of f. How is it related? I'm trying to find the derivative of f of x squared plus 1. How can I find this derivative? So, what is the last operation that I'm applying here? So this thing, f of x squared plus 1, is not a product of f and x squared plus 1. It's evaluating the function f at point x squared plus 1. This thing between f and x squared plus 1 is not a product. So it's like, it's as if I was evaluating, let's say, if f was the sign, then I would be evaluating sine of x squared plus 1. It wouldn't be the product of sine and x squared plus 1. So it's not the product. What is it? It's the composition. The last operation that I'm performing is computation of the value of f at some point, but this point is not x. This point is some expression in terms of x. So here I'll apply the chain rule with the following. U is going to be f of v, and v is going to be x squared plus 1. Now I can find what's du by dv. It's f prime at the point v, and dv by dx is 2x. So overall, I have f prime at the point v, which was x squared plus 1, multiplied by 2x. So will this step here? Why I wanted to apply chain rule, and then how I applied it. Okay. So next part is just plugging in the number that we're interested in. What is g prime at the point 3? No, I'll take this expression that I got there, and instead of x, write 3. So here I have f prime at the point 3 squared plus 1, which is 10 multiplied by 2, sorry, that's g prime of 3. 2 times 3. So instead of x, I plugged in 3. And now f prime of 10 is given to me, it's 5. Times 2 times 3, and the answer is 30. So, what's kind of surprising about this thing is you have no idea what the function f is. Just no idea whatsoever. The only thing you know is the derivative of the function f at the point 10 is 5. But there are, of course, a lot of functions whose derivative at the point 10 is 5. You can think about the graph. It means that when x is equal to 10, the slope of the tangent to the graph of f is 5. But that's the only thing you know. From after you know what the slope of the tangent at a given point is, you can continue the graph in any way. Like this, like this, like this, whatever. Then you form a new function about which you know, well, also almost nothing. You just know that it's the old function evaluated at x squared plus 1. And the new question is, what is the derivative of this function at the point 3? Well, the chain rule allows you to relate the derivative of this new function to the derivative of the old function. Once you have this relation, the rest is just plugging in the number. And one other point which, well, now seems obvious when I'm doing it, but I know that once you try solving similar exercises, you might get confused. Do not try to plug in the numbers right away. That will just confuse you. You cannot just argue that g prime of 3 is f of 3 squared plus 1 prime. That would be just wrong. Because once you plug in the number, instead of x, you plug in 3, f of 3 squared plus 1 becomes a number. And then you get confused with derivative of the function versus derivative of this number. So don't do this. It will be really confusing. There is a difference between g prime of 3 and g of 3 prime. G of 3 would be a number, and its derivative would be 0. But g prime is a function, and can be evaluated at the point 3. So the best idea, or the best way of kind of separating these two things would be first argue about the function in general, g prime of x, and only later plug in x equal to 3. This way, we have the smallest space for confusion. Any questions about this? So, let's solve such an exercise. So this exercise will lead us eventually to the next concept of logarithmic differentiation. So suppose you don't know what the function y of x is, but you know what is 1 of y of x. I tell you that 1 of y of x is x plus sine of x. The question is, find y prime of x. Well, so let's look at this question. I told you that I know what is logarithm of y of x. In a way, from here I can find what y of x is itself, without the logarithm. In fact, y of x would be just e raised to this power. From there, you will be able to differentiate y of x and find y prime of x. So let me say way 1. Y of x is e raised to the power x plus sine of x. Y prime of x is, well, apply the chain rule. E to the power x plus sine x multiplied by x plus sine x prime. So it will be e to the power x plus sine x times 1 plus cosine of x. So that would be one way. You start with the expression for logarithm of y, find what y is, and differentiate. This way is okay. I mean, in this particular example, it's not very complicated and gives you the answer. I want to show you an alternative way. So alternatively, I will not find what y of x is. I'll just work with this expression directly. I'll take this identity, 1 of y of x is s plus sine of x. After all, on the left side, I have a function of x, and on the right side, I have a function of x. And they are the same function. Once again, different expressions, but the same function. For every value of x, you get the same answers on the left and on the right. Well, it means that their derivatives as functions of x are also the same. Well, now let's find these derivatives. On the right side, I have 1 plus cosine of x. That's really simple. On the left side, I have derivative of 1 of y of x. What is the derivative of 1 of y of x? Say? Okay, yes. It is 1 plus cosine of x, but what I want to do is just simplify this expression. Simplify the expression 1 of y of x prime. E by any powers. I just have a composition of two functions, one O and another function y of x. The chain rule. So here I apply the chain rule. So here I apply chain rule with u being one of v and v being y of x. So the answer is going to be derivative of logarithm is 1 over its argument. Derivative of y of x, well, I'll have to leave it as y prime of x. So, that's what I have as a consequence of this identity. What I'm interested in is what is y prime of x. So let me solve for y prime of x. Y prime of x is 1 plus cosine of x multiplied by y of x. So without anywhere writing what y of x is, I'm able to derive the following identity. The derivative of y prime of x is 1 plus cosine of x times whatever y is. And the way I got here was take the initial equation, differentiate both sides, and apply the chain rule to find what's the derivative of 1 of y of x. So if I want to get the final answer, what is y prime of x just in terms of x, with no mention of y, I'll do the same thing. I'll find what y of x is. So y prime of x is in fact 1 plus cosine of x times e to the power of x plus sine of x. So my point here was you can directly work with derivative of 1 of y. You don't have to first find what y is and then find the derivatives. You can just work with the original expression. The reason this will be useful is, okay, so first questions about this exercise, comparing these two ways. So let me not start a new example, just tell you what the general idea will be. In this example, this way was about the same complexity as the alternative way. But as our functions will get more and more complicated, this alternative way will become way simpler than this way. And the reason will be because logarithm of very complicated expressions sometimes is really simple. Because logarithm transforms complicated operations like powers and products into simpler ones, like products and sums. So next time we'll see how to apply this trick in situation where it's actually useful. Right, so see you later. Thanks.